Define acceleration. Your definition is the rate of change of velocity. State the ball's acceleration at its maximum height. So what have we got? We've got the student standing on the top of a building that is 60 meters high, and the ball is thrown upwards at 8 meters per second, and it strikes the balcony after 4 seconds, and then it bounces and it goes down to the ground. So what is the ball's acceleration at its maximum height? When it's in free fall, which it is for this whole trip, the acceleration is always 9,8 meters per second squared downwards. Calculate the ball's velocity as it strikes the balcony. So this is going to take a little bit of effort because we've got parts to the motion. So I'm going to say V is equal to U plus AT. And I'm going to say he starts off at 8. The acceleration is, I'm going up at 8. The acceleration is negative 9,8. And it's in the air for 4 seconds, which means that in total, the velocity by the end is 31,2 meters per second, and that's going down. How do I know it's going down? Because my answer turned out to be a negative answer, so I need to make it downwards. Then I need to know, but the question wasn't that. Yes, it was. It was what's the velocity as it goes. There we go. The next thing is calculate the height of the balcony above the ground. So what I'm going to do is I'm going to work out this distance over here. In other words, the displacement of the ball when it hit the balcony. So I'm going to say S is equal to UT plus a half AT squared. Remember, all your equations of motion work perfectly well without you doing it in stages as long as you get your signs correct. So my initial velocity is 8 up. My time is 4 with no direction. A half of negative 9,8. And my time needs to be squared. When I work that out, I find a displacement of negative 46,4 meters. That makes sense because it's downwards by 46,4 meters as opposed to the direction where I made my 8 positive upwards. So therefore, I can say 60 minus that 46,4, and what's left over is the height of the balcony, which is 13,6 meters above the ground. The ball bounces off the balcony at a velocity of 27,13 meters per second and lands on the ground 6 seconds after leaving the balcony. So it's going up and it's coming down again. And we have to now draw a velocity time graph, and we have to illustrate all of these points on the velocity time graph. So the first thing to do is to say, I know I started at 8. I know that I went to the top of my projectile, and then I changed direction and I came down. I was coming down for quite a lot longer than I was going up. I don't have that information. I'm going to put some information in though. I do know that I started at A, the point where the ball left the roof. The highest point of the ball was B. The point where it strikes the balcony is C. Then we are going to get the bounce itself, and that is going to be at a slight angle going up. And what is important is that the bounce, it bounces off the balcony at 27,13. So I need to go quite a lot higher than 8. I need to go to 27,13. And that, I've made it a bit too steep over here, but anyway, there you go. So this whole green line is the bounce. The point at which the ball leaves the balcony is D. So C to D happens in a fraction of a second, obviously. And then it wants a little bit more, and it wants the point where the ball landed on the ground. So after the bounce, what is going to happen is it is going to go. So it's going to need to come back down, and this line must be parallel to this line over here. So I need 2 parallel lines over there because the acceleration is the same. It's negative 9,8 meters per second squared downwards. And then what's going to happen is, again, I'm going to stop. So this is this part of the motion. Then I need to change direction, and I need to come back on myself till I hit the ground. So I need something for this part of the motion, and we're just going to move across a little bit, and we're going to keep on coming down, 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 and we're going to get much, much faster, and eventually this whole motion ends after 10 seconds. This part of the motion was 4 seconds over there. And so when it hits the ground, we are talking about point E. During the recent Science Expo, a group of students decided to investigate how the height an object is dropped from, independent variable, affects the velocity of the object as it reaches the ground, dependent variable. I change what I measure. The students released the lead weight from set heights and used video analysis to measure the velocity of the lead weight as it reaches the ground. So, you've got the height of the drop, the impact velocity is worked out, and they ask you to work out the velocity squared. First, state a suitable hypothesis. Remember that it is always a statement, a hypothesis, and it has to link my independent and dependent variables. So something like the higher an object dropped from, the greater the velocity will be when it reaches the ground. Name the dependent variable, either the impact velocity, or if you want to say the impact velocity squared is fine. Calculate the impact velocity squared and record it in the column that is given to you. So you're going to have 4, 7,3, 11,56. So all you're doing is squaring this number each time. 16, 17,6 and 22,09. Complete the units in the column heading. And what you have to do there is you have to say, well, if it's meters per second squared, it becomes meters squared per second squared. So it's m2.s minus 2 is the unit that you would have to put over there on this table. On the graph paper, on the answer sheet, plot the graph. So you need to state graph of whatever's on the y-axis versus whatever's on the x-axis. You need to label your axes. You need to put 0 in as a point. You need to evenly graduate your axes, and then you're going to plot your points. And you get a nice proportional graph. Determine the gradient of that graph. So if you're going to determine the gradient of a graph, you're going to say y2 minus y1. And I chose the point 17,6 minus 3,2 over x2 minus x1. I used 120, and I get 0,18. And that's centimeters because I had my graph in centimeters. If you had converted to meters, you would have landed up with 18. Now we need to describe something. A straight line graph is described by y equals mx, and you guys all know this, but I don't think you can apply it that well. And then you're going to say, we also know that v squared equals u squared plus 2as is an equation of motion, and it relates to velocity squared and displacement. Well, we've got a displacement, and we've got a velocity squared. So now this is a level 4 question, but bear with me and let's see what they're trying to puzzle out. We're going to say, in comparison, I've got y equals mx plus c. What am I going to put on my y-axis? V squared equals my x is the distance, and plus c, which is my initial velocity, well, is 0, okay? There we go, 0. So I can say that that somehow relates to this particular thing, where it's v squared is equal to u squared plus 2as. So what must m be? M must be 2 times a. So I can take my gradient, which is going to be 0,18, or if I'd used meters, which maybe would have been smarter, I would have got 18. If I divide that in half, 2 times 18 is my gradient. So I need to divide that by 2 just to get the acceleration, and I find that my answer is around about 9 meters per second squared. So you can look at that and you can see quite clearly how that relates to a straight line graph. Suggest why the value obtained from the graph is different from what you expected. Obviously, you expected this to be 9,8 meters per second squared, and then you need to use your descriptions of air friction, human timing error, all the things that we have discussed when we've done this experiment about 4 times over the years.